Great. So I'm going to continue with the positivity of the last talk and talk about another PSA. So I think in the first talk, the take-home message was like, write unit tests. I think in this one is a much bigger problem. And I think the core of the problem as we get to at the end is how do we establish trust from the underlying maths and theory behind things through its communication to different stakeholders? And when should we be comfortable? Is there like a lot of echo here? Is that, no? Okay, it's just like right here it is. And when can this trust break down, leading to techniques being used in practice that are just, don't do anything, basically. They're not private at all. In particular, we're going to talk about a thing called input obfuscation. So has anyone in the room come across input obfuscation before? Okay, like one or two, a few hands. So I'll describe what it is and like the general approaches. This definitely isn't to pick on any individual technique. And I actually think that the takeaway could be two different things. The takeaway I don't want to come across is any sort of criticism of like innovation and people trying new things. And maybe the criticism that I do want to take away is that we should be very careful about the techniques that we try to put into practice in industry under the allure of security and privacy when the verdict is out on whether or not they actually achieve that. And I think that it's kind of like a PSA more than a innovation or breakthrough. So privacy in machine learning has different parts, right? So the one that I think is often talked about is during training time. So you have a big source of data, you want to train a machine learning model, and in doing that, you don't want to learn from the original data in such a way that you might like leak information about the data subjects, etc. But of course, there's the second half of that, which is, hey, I like using Anthropic or OpenAI or Gemini for the Googlers here. I know there's a lot of Google people. But I don't necessarily want to share my data, right? So like I know it says at the little bottom, like your data will not be used for retraining. But also this talks about how people are trying to use differential privacy to get insights to obviously improve their models and stuff too. So there's kind of a balance. So ideally, if I could just send up something to the LLM providers, et cetera, that contained no information or that I was completely anonymous about, that would be like a super big win. And obviously there are some techniques that are kind of well established to do that, but they usually require either cryptographic overhead or some like physical hardware to achieve it, like confidential computing, as opposed to the techniques kind of addressed here. And the growing line of tool claims to protect inference inputs is basically going to be the subject of this talk. In particular, input obfuscation. So the idea is that wouldn't it be great if I could like write my questions to Gemini or Claude or whoever, and I could just feed them through, I could basically get the tokens produced, I could feed them through a proxy, which would do something to it, and then that something would in some way preserve the privacy of my internal prompt, yet when I send it forward to the LLM providers, they would still be able to process it in the same way and return to me useful results. Right? That's the kind of premise of input obfuscations. There's a number of papers that emerged, some like peer-reviewed, but then like counter papers came out that were kind of more critical of them. Some on archive but not peer-reviewed yet have received tens of millions of dollars and are in like national contracts with armed forces and stuff like that, when maybe we should question that. So some of the papers, if you were to like look it up, there'd be Shredder, Cloak, there's the stained glass transform. And then there are differences between these. But if you kind of look more broadly in the space, then there's things like InstaHide, Disco, there was the least privilege attribution obfuscation. And also the positioning of these papers can be quite different. So in some cases, they're quite aware of the limitations of what they can offer, and in some cases, the reporting and communications around them is kind of in a different direction. So the real question is, does it sound too good to be true? Can I just throw a proxy in front of my prompts, mix up the tokens in some way, and we have privacy? So most of the statements of where the belief of privacy comes from is wrapped in information theory. So there's, again, different styles, but it usually breaks down to mutual information on things like packet privacy, etc. So how can we even think about this? Obviously, in a signal, so like a prompt or something like that, there's information content. The actual bits you need to pin down that just like are the core of what you're trying to communicate. And that's, there's some amount of entropy or information associated with that. And then, of course, we can take processes. So you can do something, anything, to that signal, and you'll have some output. And that, again, will have some information associated with it. And so you can describe the relationships between these as mutual information or conditional information. And if you ever pick up an information theory textbook or something, one of the first things you're going to come across is the data processing inequality. And I realize this is quite a mixed audience. This deck originally had lots of equations, and then I threw them all out this morning, so there's no equations in this. But the analogy that I think is, even for people who might not be from a technical background, is that if we think of information as like water, and we have a pipe, well, water comes in the top of the pipe, it goes out the end of the pipe, that would be like information perfectly preserved, right? If there was a leak, then water might seep out, and you might arrive with less water at the end of the pipe. And so the relationship between like how much water went in and how much water went out is kind of your mutual information. And when you apply a mechanism, so for example, if you were to add noise, like you might do in differential privacy, etc., these things can act as like a bottleneck, so they can kind of create leaks intentionally by design. But the data processing inequality is just really simple. It just says there can't be more water coming in than goes into it in the first place. And actually, you can look at most of these techniques quite abstractly from just by literally applying DPI, and you can quite quickly say to yourself, oh, all my information must be preserved. And so in this talk, we're going to have a few like little obvious mental exercises that I think will prove that to you, but hopefully will also, when something like this comes up in the future, the intuition will be there, irrespective of where you come from the technical, non-technical kind of spectrum. So the first one is really obvious. So if you open your favorite LLM today and you say, hey, repeat back to me this exactly, and you just add more and more bits of just random like code or whatever, it's really good at basically copying and pasting that in the result, right? Thanks to its like attention model, etc. Makes very, very few mistakes. If you think of it in terms of the edit distance, so like if a space was introduced, there'll be an edit distance of 1, because like 1. I ran these little toy tests, and like it's almost always 100% perfect. Sometimes the space is introduced or something. Like these things are like so good at this point. And so if you say to yourself, well, how much of the information can be, from my prompt, can be preserved through to the result, the fact that you can put arbitrary strings and it returns it to you means that the general purpose models are incredibly good at being bijective, of maintaining the information from the prompt through the process, right? So that's like a hint to you that if you were to put something in between and that thing was to reduce the information in a meaningful way, well, the model shouldn't be able to do a very basic function that the model can do right now. The second part of the question, and this is kind of a consequence of this, is very often when we talk about like adversaries in privacy or security, we think about what an adversary could potentially do with reasonable computation and context, etc. So what would an adversary actually look like? Probably a person who might have some intuition on something, or a computer that could run some program, right? And what would they likely do? They would probably process it to get some result. So when you say to yourself, well, if I put an obfuscation layer in front of my inputs, from the output, does an adversary exist who can process the result of that? Well, of course, because otherwise you wouldn't have the LLM, right? The LLM wouldn't be able to do the one job that it's supposed to do. So there's no difference between the LLM just doing its job and an adversary, because it is literally the same thing. So the fact that the model provider can compute on the quote-unquote ciphertext implies that an adversary obviously can. Anyone who intercepts it from that perspective then can also process it. Anyone who reads the logs can also process it, and so on and so forth. This is in contrast to things like, you might say, well, what about traditional cryptography, right? Because you can encrypt things, and then you can decrypt them. And that is true, but really within the field of cryptography, there's kind of two flavors. There's information theoretically secure, and there's computationally secure. Computationally secure usually relies on a hard maths problem that's hard to reverse, just in practice, whereas IT security usually involves the destruction of information through essentially noise in one form or another, or one-time pads or something. So, again, if there's no cryptographic mechanisms that are well used under the hood, that should also be a little, your ears should perk up. The third thing this is just very obvious, but it's obvious when someone says it, but perhaps not necessarily off the top of your head. So my name is Jack, as I was introduced. So you could say to yourself, how much information is in my name? Any guesses? I actually don't know. We could say, well, we could think of all possible names, and let's say all names have 10 letters for a first name. I apologize if someone in the room has more than 10 letters in their first name. That could be possible, but let's just make that as a construct. And how many letters are there in the alphabet? Well, let's say if we were to combine, I don't know, some extra characters, because different languages might use different characters, let's just say 30. So that means potentially there are 30 to the power of 10 possible name strings. But no one is called QQQQQQQQQQQQ unless, a billionaire has another kid or something, but that's maybe a separate conversation. But we can go lower than that, right? So that's a very high bound. So can we go tighter than that? Well, we could say how many humans have ever lived on Earth, ever, including in history. And the answer to that is there's about 117 billion. So how many bits are in that? Well, 37 bits. So we've just gone down from 49 bits to 37 bits. But you can see, I haven't met anyone here called Jack, but I would be surprised if there wasn't a Jack or John or James or something that's kind of a synonym. I don't know. I'm sure there's people in the room from the birthday problem who have the same name. So not everyone on Earth who ever existed has a unique first name. So these are obviously lower bounds. And so trying to work out how much information in a signal is really hard to do. And so often we use proxies for that. And we usually use quite loose bounds as those proxies. And what gets reported is reductions in those loose bounds. So if I was to say, well, we've managed to reduce from 37 to 27 bits, you might say, oh, wow. But actually, maybe the core information has 15 bits or something, right? That would be totally possible. And so that reduction in perceived information might actually be completely meaningless. And this, believe it or not, is exactly how the results are reported. So this is not made up. This is in one of the papers. And they say, we can show that we've reduced information in the obfuscated signal from the original input because there's 4,096 dimensional vectors in the embedded space, and we tokenize each bit of your text, each couple of characters, into one of them, and we add noise to every single dimension in that. And so we can reduce it from any float down to a handful of bits. I think they say 2 nats, which is 5 or 6 bits or something. So you have 5 or 6 bits times 4,000 dimensional space. So you have about 50,000 bits of information, which they've brought it down as the lowest upper bound. If you actually look at any of these models, they actually only have 2 to the 17 tokens. So for somebody to say, hey, we've managed to bring down the amounts of bits of information down to 50,000, but there was only ever 17, it's a total misnomer. It doesn't mean anything. It means they started with an incredibly loose bound in the first place, which means they're probably not doing anything, especially if the model still works, thanks to the smell tests we talked about earlier. So what are the things that seem to be common patterns? And by the way, I don't want to imply that we've come up with these. These keep appearing in literature as people are oh, this technique failed for one reason or another. But it's typically one of 4 kind of causes. So the first one is that the real measure is intractable, and sometimes it's just not defined in the first place as well. So InstaHide, that was really popular, it actually won the Bell Labs Awards, I think. It was an ICML paper in 2020. It got lots of recognition, and then Carlini went heavy on it. Was very wrote very strongly opinionated blogs and papers following up on it, saying how could this possibly have won any awards, etc. Because the adversaries weren't defined in the first place, and so the problem space wasn't really defined. So that's a very big problem. The second is empirical estimates, and so you have very loose bounds in the first place, and you're trying to reduce these loose bounds, but it doesn't give you a meaningful guarantee that you can actually work with. Another one, which you see actually a lot, is when people talk about entropy in the training loss of training some sort of neural network or something. But you have to remember what a loss function is when you're training a model is kind of a reward. You're saying, good job, model, keep going, right? So especially in supervised learning, when you're trying to train based on a task, it's usually based on some sort of accuracy or something like that from the labeled data. And essentially what you're doing is saying better job you do, pat on the back, but as our estimate for entropy goes up, opposite of pat on the back, right? And you need to balance these two things. But that doesn't actually lead to any meaningful guarantee, which means you can end up with a model that you think you've trained with meaningful metrics, but actually you haven't really done anything at all. And finally, and this is by far the most common, it's here's a bag of attacks that we found from other papers, so we're just going to apply them to some example outputs, and it wasn't immediately linked back to the original data, therefore it's safe. And I think that this has come up in previous talks at this event and others in the past, where just using kind of a bunch of known attacks, they tend to be very general because they kind of have to apply to everything. So it's not a great way to claim privacy or security. There is a very simple test as well when you look at some of the metrics, especially for the estimation of information and mutual information between the signals. And a very simple one in language is if you take the original sentence and you just translate it randomly to Japanese or I don't know, Arabic or something that's just functionally looks very different, and you pass them through the same tests, you can often get back reported high divergence. It's oh, this is appears to be so random. Whereas actually a polyglot who just happens to know the world languages would easily be able to rewrite them back to its original form. So that isn't a security mechanism, but it's enough to be able to trick a poorly crafted loss function. So there is actually real benefit, and some of the papers, I think, have done a good job in communicating this. And it's very easy to understand this as well. So I can write a big, long prompt that contains a lot of information. But if the LLM is not being used for the purpose of being able to answer any arbitrary question, but rather something really specific, is there a name in the prompt that comes into us? And it's a yes, no answer. Well, a lot of the text from the original prompt probably isn't that valuable. So you might have loads of words in there that are definitely not names. So you could just throw all of them in the bin, and it wouldn't really change the result. And so that intuition is the same for the input obfuscation methods. So when it's claimed under the context of, hey, let's take a general model, let's tighten it so it can only be used for a narrow task, and then let's obfuscate and reduce the information in the original input signal, that is basically data minimization, which is promoted under GDPR, et cetera. So there is real-world use, but we have to be really careful from separating real-world use and value, for example, creating very narrow tasks from potentially general ones, through to the claims that are openly marketed and sold, which is just, I think, irresponsible. Now there are, 1 minute. So there are techniques which aren't like this. I think differential privacy is the obvious one, but I can't make my prompts differentially private, otherwise my prompt will be like a randomly flipped coin or something. It's just not going to be that useful as an input guarantee. But when we think of them under the guise of mutual information, they actually have really clean relationships. So your mutual information grows linearly with row, for example, in zero concentrate DP. And for membership inference, you can even like kind of think about the number of bits because, well, there's very clean relationships. So it's like a meaningful thing. The main takeaway I was going to say is just what actually can protect your data at inference are things like confidential computing. Of course, you still have to trust the software and like the physical servers, et cetera, too. Differential privacy, which I think is well established as one of the kind of gold standards. On-device inference, so like don't actually take the data off the device in the first place. And of course, there's things like homomorphic encryption, secure multi-party computation, et cetera. The one word of warning, and it goes back to the tests in the last talk, but also with TEs, homomorphic encryption, SMBC, et cetera, is it's not heavily standardized and widely used. And so the risk associated with, misimplementations is still high. So like encouraging to use PETs, but also maintain like a high bar before you build your confidence around them. Okay.